Good morning, students. In this video, we will discuss about monotonicity and extremum, that is maxima and minima. As we have already studied about continuity, differentiability, and about functions. So, what is the need of monotonicity? So, to understand any function f of x, what we discuss about its continuity, differentiability, and remaining parameters, whether the function is even, odd, and so many things. But the most crucial and significant parameter is its monotonic behavior. Without knowing its monotonic behavior, we cannot know all the things about a function. So that is the necessity of monotonicity. So when we will say a function is monotonic, suppose we have a function f of x. When the function is either increasing or decreasing, in its entire domain, we will say that the function is monotonic. What does monotonicity means? That the function has the same kind of behavior, that is either increasing or decreasing. For example, if we take e power x, and if I plot the graph for e power x, is like this. So we can see from the graph that the function is increasing. If we take log x, the graph for log x is like this. So here also it is increasing. Now, if we take another function sin x, so whether if I draw the graph of sin x, the graph of sin x goes like this. So here we can see that the graph of the function sin x is increasing, then decreasing, increasing, decreasing. So I cannot say here that the function is not monotonic. So it's not monotonic, it's non-monotonic. If we take the graph for e power minus x, the graph of e power minus x is like this. So here we can see that the values are decreasing. So when the function is either increasing or decreasing, so we can say that e power minus x is monotonic. If I take minus of x cube or x cube, so minus of x cube is the graph will be like this. So here also we can see that the values are decreasing. The function is decreasing. The curve of the function is decreasing. So it is monotonic. In the case of non-monotonic, the function is both increasing or decreasing. As I already have discussed, graph of sin x. So the graph of sin x goes like this. So here we can see that from 0 to pi by 2, it is increasing, then pi by 2 to pi, it's decreasing, then again it's increasing, decreasing. So it is non-monotonic. Next, if I take the graph for y is equals to mod x, graph of y is equals to mod x is like this. So here it is decreasing, then increasing. So it is also non-monotonic. So for a function to be monotonic, it is very necessary that it should be either increasing or decreasing in its entire domain. So the function should be either increasing or decreasing in its entire domain. Now we will talk about the monotonicity, whether the function is increasing or decreasing around a point A. Suppose I have a point x is equals to A. So we will know how we will find that the function is increasing or decreasing around the point x is equals to A. With the help of graph, we will see it. Suppose we have the curve like this, f of x, and here we have a point x is equals to A. And in neighborhood, we have 2 points, different points. X is equals to, here this point is A minus h, and here this point is A plus h. So from the graph, we can conclude that we can see here that the function, the graph of the function is increased, the values are increasing. As x is increasing, the f of x is also increasing. So from here, we can conclude, we can see here that the value at x is equals to A, and it means this value, which means f of A is greater than f of A minus h. And f of A is less than f of A plus h, which means I can write it as f of A plus h is greater than f of A. So if these two conditions are satisfied by the function f of x, then we can say that the function at x is equals to A is increasing, where h is a positive, where h is a very small positive number in the neighborhood of A, and we have to conclude here that this h, or the continuity, that it is continuous in between A minus h to A and A to A plus h. Similarly, if I take the graph like this, suppose here the point is A minus h, this point is A, and here the point is A plus h. So if we are talking about this point, x is equals to A, x is equals to A. From the graph itself, we can see at f of A minus h, which means the value at x equals to A minus h, f of A minus h is greater than f of A. And f of A is greater than f of A plus h. So from here, we can conclude that it is monotonically decreasing if these two conditions are satisfied. So if these two conditions are satisfied, we can say that the function f of x is monotonically decreasing at the point x is equals to A. So with the help of these conditions, we can easily tell about a point that at that particular point x is equals to A, f of x will be increasing or decreasing. Next point is, whether is it necessary that the function should be continuous, like we have to consider the continuity or differentiability of the function in that domain, yes or no? No. For determining, suppose I have a graph like this. So here, suppose we have a point x is equals to A. So here we can see at this particular point, the function f of x is not differentiable. Not differentiable. But still we can say that at x equals to A, the function is increasing. Similarly, suppose if we have the values like this, if we have the function like this, so here also if we take this point as x equals to A, so here we can see the function f of x is discontinuous. But still we can say that at x is equals to A, f of x is increasing. If I take the symbol for increasing, so we can say that f of x is increasing. Now I will talk about for the interval x1 to x2. Suppose we have interval I, which is x1 to x2. So for the interval x1 to x2, how we will determine that the f of x is increasing, decreasing, or strictly increasing, strictly decreasing? Suppose we have x1 less than x2. Here we can see that this is an open interval, and we are taking that x1 is less than x2. But for this, if we are getting f of x1 greater than f of x2, what does it mean? It means that when x1 is less and x2 is more, but at x1 we are getting more value and at x2 we are getting less value. So it is strictly decreasing. Strictly decreasing. So graph for this will be like suppose we here have some value x1 and here we have some value x2. So here we can see that at x1 the value is more, at x2 the value is less. So this is for strictly decreasing. Now suppose if I take x1 less than x2, and f of x1 is greater than or equals to f of x2. What does that mean? At any point, it may be possible that the function's value is not changing, that the values are coming same. So in that case, we will say that the function is monotonically decreasing. Suppose we have a function f of x and its graph is going like this. So here we can see that at some x1 and x2, the value may be equal. So in this case, we say that the function is monotonically decreasing. Now we will talk about, suppose we have x1 less than x2, but we are getting as f of x1 is less than f of x2. What does that mean? That as x is increasing, the value of the functions f of x is also increasing. So what does that mean? That means that the function is strictly increasing. So what does it mean? If I draw the graph of f of x, suppose for x1 and x2, so it will be strictly increasing like this. So here suppose I have x1 and here I have x2. So clearly we can see that the value at x2 is more and x1 is less. So here it is strictly increasing. Now suppose next case we have x1 less than x2 and we are getting f of x1 less than or equals to f of x2. What does that mean is at some particular point, it may be possible that the function is getting same value at two different points. So in that case, we will say it is monotonically increasing. So in that case, the graph will be like this. Here we can see at some point, it may be possible that the values are same. The graph is still here also the graph is increasing, but at some point it may be possible that f of x1 equals to f of x2. Then we will say it is monotonically increasing. Now we will try to understand what is inflection point. So first we discuss it with the help of f of x is equals to x cube. We know the graph for f of x cube is like this. So at x is equals to 0, if I differentiate it, dy by dx is equals to f dash of x is equals to 3x square. So we can see at x is equals to 0, the slope is 0. But the concavity of the curve is changing. So these points are called point of inflection. This point is point of inflection. So point of inflection is the point where point of inflection is the point where double derivative of the function f dash of x naught is 0 or does not exist. But f dash of x naught exists. For y is equals to x cube, we can see if I differentiate it, dy by dx is equals to 3x square equals to 0, which implies x equals to 0. If I differentiate it again, we get d2y by dx square is equals to 6x, which is again 0. So from here we can see that at x not equals to 0, which means at x equals to 0, the double derivative is also 0. So this point is known as point of inflection, or the point of inflection is the point, or point of inflection is the point where the curve changes its concavity. So what does that mean? It means that the curve will change its concavity. It will go from concave upward to downward, or concave downward to concave upward. If suppose we have x belongs to a to b and our double derivative d2y by dx square is greater than 0. So what does that mean? It means the curve is concave upward. So if we draw the graph for this, it will be like this, upward between A and B. It's a concave upward. If we have d2y by dx square less than 0, it means it will be concave downward. So for concave downward, we have d2y by dx square less than 0, or we have the graph like this. So with the help of this d2y by dx square, we can find whether the curve is concave upward or concave downward. As I have already discussed about y is equals to x cube. Suppose we have a graph like this. And this point is x is equals to c. So here we can see at x equals to c, the function is changing its concavity, right? It is going from concave upward to concave downward. So we can say here at x equals to c, we have point of inflection. Now we try to understand what is the extremum. So how we define local maximum, local minimum, and all these things with the help of first order derivative, second order derivative, nth order derivative. So we will discuss now extremum, local maxima, and local minimum. So first we will try to understand with the help of a curve. Suppose we have a curve like this for f of x. Here we have a point A. Here we have a point A minus h, and this point, some point here is A plus h. So here we can see at the point A, the value of the function, suppose this function is f of x. F of A is greater than f of A minus h. And f of A is also greater than f of A plus h. So we can say at x is equals to A, the function f of x has local maximum. Similarly, suppose we have a graph like this. A plus h, here we have some A minus h. This is for f of x. So here we can see that f of A, at f of A minus h, the value is more, f of A, the value is less, and again at f of A plus h, the value is more. So in the neighborhood of the point A, the values are more, and at the point A, the value is less. So mathematically, we can write it as f of A is less than f of A minus h, and f of A is less than f of A plus h. What does that mean? That means that at the point x is equals to A, the values are less. So we can write it as, here we have a local minima at the point x equals to A if these two conditions are satisfied. Now we will discuss about first order derivative test. What is first order derivative test? With the help of first order derivative test, how we can determine whether we have maxima, minima or not. Suppose we have a function f of x whose graph is like this. Here we have a point A. Here we have a point A minus h. Here we have a point A plus h. Similarly, here we have a point B. Here the point is B plus h, and here the point is B minus h. Now we will try to understand this, and this is the graph for f of x. So if we go from A minus h to A, if we are moving from A minus h to A, we can see here that the values of the function are increasing. So here the slope is positive in this region. dy by dx is greater than 0. Now, if we come here, the values of the functions are decreasing from A to A plus h. These values are decreasing. The slope is decreasing. So here we can say that the function values are decreasing. dy over dx is decreasing. And at this point, we can say that from here to here, the slope is positive, here to here, the slope is negative. So at this particular point, dy by dx is 0. Similarly, we can see here from b minus h to b, the values of the functions are decreasing, which means the slope is decreasing. From b minus h to b, the slope is decreasing. And again from b to b plus h, it's increasing. Here it is decreasing, here it is increasing. So at this particular point, the slope becomes 0, which means here also the dy by dx becomes 0. So what is the essential condition? So from first order derivative test, we can conclude that for maxima and minima, here we can see that the condition for this is maxima and here it is minima. For maxima and minima, we are getting for maxima and minima, the conditions which we are getting from the graph is dy by dx is equals to. So this is the condition for first order derivative test. Now we will talk about second order derivative test. Second order derivative test. Suppose we have the same graph for f of x. Like this. So here we have a point A. Before that we have a point A minus h. After that we have a point A plus h. This is our graph for f of x. Here we have a point B and again same points B plus h and B minus h. So from here we can see that from A minus h to A, dy by dx is positive. After that, dy by dx is 0 at this particular point at x equals to A. And after that, dy by dx is slope is decreasing. So for here we are getting a maxima, we know that. So from this what we can do, that we can clearly see here that the slope is continuously a decreasing function. First it was positive, then it was 0, then it was decreasing. So what we can say, it's a decreasing function. If the slope is a decreasing function, for decreasing function we know that the slope of the decreasing function is less than 0. What does it mean is dy by dx, dy dx of dy by dx is less than 0. So from here we can write d2i by dx square is less than 0 for maxima. Similarly, from b minus h to b, the dy by dx is decreasing, which means dy by dx is less than 0. Then at x equals to b, the dy by dx is equals to 0. And x equals to b plus h, dy by dx is greater than 0. So here we can see that the slope is continuously increasing. And for increasing function, we know that the function slope of the function is dy by dx of that particular function is greater than 0, which means dy by dx of dy by dx is greater than 0, which means d2i by dx square is greater than 0. So this is the condition for minimum. we have the graph like this. So for at this point, we can see this the condition at point x is equals to b. Before that, we have the point b minus h, and after that, we have the point b plus h. So this is the condition for minimum. Thank you. I hope you have enjoyed learning monotonicity and maximum minimum concept. We will continue it in the next class. Thank you so much.